Hello and welcome to this video. Today I'm going to talk about how to generate simple random maps. What I mean with this is to generate images that look like this, where we have green areas, such as this area over here, that looks like a continent, and other areas that look like islands. And we also have blue areas that kind of look like oceans and basically seas. So how is this possible? How can we create an algorithm that generates these images? So what we use is another algorithm called Perlin Noise, which is not exactly the same thing as random noise, because random noise, the colors are basically randomly generated. There's no relationship between colors of close pixels, while in Perlin Noise we see a relationship between the colors of a pixel and the pixel besides it. So now I'm going to explain you how the Perlin Noise algorithm itself works. So we first start with a grid with an arbitrary number of squares. So all of the squares have a size which can be defined by this IVD variable, which stands for intervector distance, and you're going to understand in a while why I called it like this. So the first step in the Perlin noise algorithm is to generate random vectors. So basically we try to generate random vectors for each one of the corners of the squares which we see right here. So basically we have a certain size which in my implementation is the same for all of the vectors, so the magnitude of the vectors is equal for every single vector. And we basically have a random direction associated with each vector. So this could be implemented in multiple ways. One of them is doing a process that looks like this, which is basically trying to generate a random angle between 0 and 2 pi radians, which is the same thing as saying generating a random angle between 0 degrees and 360 degrees. And then we apply some trigonometric operations to this angle in order to obtain the coordinates of the vectors themselves. So once we have all of the vectors generated, what we need to do is to calculate dot products. So here we have the grid with the random vectors. And since the process of calculating dot products is the same for every square in the grid, I'm going to be focusing on one square in specific. So let's look at this square. So the process of calculating dot products, it needs to be applied for every point within this square, but I'm going to focus on one point in specific. So let's select a random point. So let's select this random P point. So the first thing we do is to calculate some displacement vectors between this point and each one of the corners. So these vectors right here. And to make the calculations easier, I'm going to give a name to each one of these vectors. So the letters below stand out for the direction of the corner. For example, NW stands for northwest, while NE stands for northeast. So what we do now is to calculate the dot product between each generated vector and its equivalent uh, displacement uh, vector for each corner, let's say. If you don't remember how to calculate the dot product, let's imagine the dot product between these two vectors. What we do is to multiply each of one of the coordinates and then add them up together. So it's a simple operation to be done. And at the end we have the dot product. For example, in this case we have a dot product of 30. So in case you are curious to how the dot product works, so if we have two parallel, actually two perpendicular vectors, they will have a dot product of 0. While if we have um, vectors of opposite directions, they will be at their minimum values, and vectors pointing at the same direction will have their maximum value. So at the end, we will have a dot product value associated with each one of the corners of the square for each point. And if we want to visualize this, we could remap the dot product value onto a color. For example, we could remap the lowest value to the black color and the highest value to the white color, and then all of the colors between would be the other values. And it would generate an image that looks like this. And if we zoom in to the first squares, we could sort of guess the direction of the vector just by looking at the image. So, for example, this vector over here with this square, which this is the northwest corner of this square, we see an increase in the color in this direction, as in the same direction of the vector as we can see here. We see an increase from a kind of like grayish color onto a color that is closer to white. And the same thing happens in other squares. For example, in this one over here, we see an increase in this direction, while in this one over here, we see an increase in this direction. And basically, this is what the dot product operation does. It kind of generates a gradient of colors uh, based on the direction of the vectors themselves. So the final step of the Perlin Noise algorithm is to interpolate these dot product values. So we have the dot product values for each one of the corners, and what we want to do is to somehow join them to generate a final height value for the map. So how can we do that? So what we could do is to first interpolate the north corners into an interpolated north value, and do the exact same thing to the south corners, and then interpolate these two values to generate the final height value. So now explaining the interpolation process itself. Basically here we are trying to interpolate the north values, and what we first need to do is to calculate this percent value, which is basically the percentage in terms of distance from the point P and the corners uh, in terms of percentage and not in terms of value. So the the interpolation formula itself looks like this, and if you want to get a feel to how the interpolation formula works, you could look at a graph like this. I'm not going to try to explain you since it's a bit abstract. Just look at it. Um, so basically, after we do the interpolation process, we will have the interpolated value applying the formula, and we need to do the exact same thing onto the south corners to get the interpolated south value, and the exact same thing is done with these two variables, but the percent value, instead of being in terms of the x variable, we are trying to talk about the y variable. So we use the exact same formula. That percent is different, of course. Now, there's a thing. We are trying to do linear interpolation, which looks like this, but to get a smoother map, we should use another type of interpolation, and for that I'm going to use a type which uses a smooth function. The only change we are doing here is by applying a smooth function to the percent value, and an example of a smooth function would be something that looks like this. So basically this just smooths the map to make it look slightly better. So basically at the end we would have the height values for each point, and you could remap those height values to a set of colors, and you would generate an image that looks like this. But still, this image doesn't quite look like the map that I showed you at the beginning. So what can we do to achieve this map? So the first thing to do is to remap to a different set of colors, and this will generate a different map, and it looks like this. The thing is, we see that the coasts of these islands, for example, they are pretty smooth, and the size of each continent, let's say an island, is it's not ideal for what we want. So remember the IVD value, which I talked about at the beginning, the intervector value. If we change this value, we basically get different sets of maps. For example, in this case, we see a map which has big continents but small variation in terms of the coast. While in this map, we see, let's say, small islands and small continents, but this is not what we wanted. None of these maps fit what we want. So what we do is to add up these maps. So add up the heights of these maps together. And what we will get is something that looks like this. And it still doesn't fit our needs. It looks kind of like what we wanted, but it's not really what we wanted because there's too much variation. So this is because the map with the lowest intervector distance value is causing a lot of variation in this map. So what we could do to fix this problem is for maps that have a lower IVD value, we need to also have a lower height variation value on that map. And how can we do that? So when we are adding up the heights of all of the maps, before adding up those heights, we multiply each one of the maps by a certain factor. This factor is applied to every single height for every single point, and basically this generates a much better map, a map that looks like we want it. So now I'm going to show you a little bit of the code that generates these maps. Basically, this instruction over here generates a Perlin map with this width and this height and an intervector distance of 300. This one over here generates another Perlin map with 50 for the intervector distance. And this one over here basically generates a map with 16 of intervector distance. Before adding up the maps themselves, we need to multiply the map by the factor which I talked about. And then we need to basically add up the maps and generate the color map, which is done using these instructions over here. So if we run the code, uh, just to give you an example, this will take a little bit of time. But we see it generated another uh, uh, random map, and we could be here tweaking a little bit of the values to see what we could get, and we would get different types of maps. For example, if I lowered this intervector distance value, we would get a slightly different map. Let's look at it. So let's generate. So basically lowering the intervector distance will make the continents smaller, so it will look slightly different than it looked before. So let's wait for the code to run. And now, yeah, as we can see, the continents are smaller. And yeah, basically this is what I wanted to show you. So I hope you liked this video. Please subscribe to my channel if you like my content. And I will try to make the code available. I'm going to put a GitHub link on the description. And I hope you all have a great day. See ya!